It is the greatest light show on Earth. A silent, celestial ballet of impossible color and motion. Ethereal curtains of emerald green, violet, and crimson red, shimmering and twisting in the dark as if the heavens themselves are alive and breathing. For millennia, we have looked up in awe, fear, and profound wonder, telling stories to explain the magic unfolding above us. This is the Aurora Borealis, the Northern Lights. But what is it really? Is it a glowing bridge to the land of the gods? The spirits of our ancestors playing a game in the afterlife? Or a mythical fox painting the sky with the sparks from its tail? For nearly all of human history, it was a profound and beautiful mystery. What truly causes these lights? Why are they green and on rare nights, a ghostly red? And most importantly, how can you plan a trip to see this breathtaking phenomenon for yourself? Our story begins, as so many do, with the sun. It's not just a benign ball of light. It's a churning, chaotic nuclear furnace. A 10,000-degree Fahrenheit ball of plasma, constantly boiling with magnetic energy. And it's always shedding. The sun's immense gravity can't hold on to everything. It constantly and in every direction releases a supersonic stream of charged particles, mostly electrons and protons. The solar wind blows through the entire solar system, traveling at speeds between 1 and 2 million miles per hour. But thankfully, Earth has a shield. Our planet's molten iron core acts like a giant dynamo, generating a powerful, invisible magnetic field, the magnetosphere. It's a protective bubble, stretching tens of thousands of miles into space. This shield deflects the vast majority of the solar wind, protecting our fragile atmosphere and all life on Earth from being scoured away. A solar flare is a massive, instantaneous burst of radiation, but a coronal mass ejection, or CME, is the real heavyweight. It's a colossal explosion of magnetized plasma, billions of tons of solar material, hurtling through space. When one of these storms is aimed at Earth, it slams into our magnetosphere like a tidal wave. The impact is so powerful it compresses the field on the day side and dramatically stretches it on the night side, triggering what we call a powerful geomagnetic storm. During this storm, the charged particles of the solar wind are captured by Earth's magnetic field. They are funneled, like rainwater following gutters on a roof. These particles are guided along the planet's magnetic field lines, which all converge down towards the planet's north and south poles. This is why auroras don't happen in Hawaii or Egypt. They are concentrated in two great rings, or halos, around the magnetic poles. We call these the auroral ovals. So now we have this river of high-energy solar particles, electrons and protons, speeding down Earth's magnetic superhighways at thousands of miles per second, aimed right at the poles. And what do they find when they get there, 600 miles above the ground? This is the main event. These particles, energized by their long journey from the sun, finally slam into the atoms and molecules in Earth's thin upper atmosphere, mostly oxygen and nitrogen. When they collide, they transfer their energy to these atmospheric atoms, exciting them, which is a polite way of saying they knock an electron into a higher energy state. But an atom doesn't stay excited for long. It's unstable. To return to its normal stable state, it has to release that extra energy, and it releases it in the form of a tiny particle of light, a photon. Now multiply this one collision by trillions upon trillions upon trillions, happening every second over thousands of square miles. And you get the aurora. Okay, so collisions create light. But why the different colors? Why is the aurora almost always that iconic green, but sometimes red, or even fringed with purple? The answer is a beautiful mix of chemistry and physics, all happening at different altitudes. Think of it like a cosmic neon sign. When you make a neon sign, you fill a glass tube with a specific gas, like neon, and run electricity through it. The gas atoms get excited and glow a specific signature color. The atmosphere is just a giant, invisible tube filled with different gases at different altitudes. The electricity is the solar wind, and the gases are oxygen and nitrogen. The most common color you'll see, that brilliant, iconic green, comes from oxygen atoms. When a solar particle hits an oxygen atom at an altitude of about 60 to 180 miles, 100-300 kilometers up, the excited atom releases its energy as a greenish-yellow photon. At this altitude, the atom has just enough time, about 3/4 of a second, to glow before it bumps into another atom. Our eyes are extremely sensitive to this specific shade of green, which is why it looks so incredibly bright to us, cutting through the darkness. But what about red? Red auroras are much rarer and are also caused by oxygen, but at a much higher altitude, from 180 to 400 miles. Up here, the atmosphere is incredibly thin, almost a vacuum. The oxygen atoms are so far apart that after they get excited, they can float around for up to 2 minutes before releasing their photon of light. This is a very slow-release, forbidden state, and it produces a deep, ghostly, blood-red color. This often only happens during very intense solar storms, and you'll typically see it as a faint, eerie red glow high above the main green curtains. So, what about the pinks, blues, and purples? Those fast-moving, vibrant colors are the signature of the most common gas in our atmosphere: nitrogen. When high-energy solar particles penetrate deeper into the atmosphere, to altitudes around 60 miles or less, they slam into nitrogen molecules. Nitrogen doesn't wait. It gets excited and releases its light almost instantly, in a flash of blue and violet light. When that blue and violet mixes with the more common green, or sometimes with a bit of red, our eyes perceive it as a bright pink or magenta fringe on the bottom edge of a very active, fast-moving curtain. So, when you look up at the aurora, you're not just seeing pretty lights. You're a spectator at a celestial chemistry lab. The colors you see are a real-time diagnostic, telling you what gas is being hit, where it's happening, and how much energy the sun has thrown at us. Long before we understood the science of atoms and magnetospheres, humanity tried to make sense of the awesome and sometimes terrifying lights in the sky. To the Norse peoples, the aurora was a sign from the gods. Many believed it was the Bifrost Bridge, a glowing, flickering archway that connected Midgard, our world, to Asgard, the home of the gods. Others believed the lights were the reflections flashing off the shields and armor of the Valkyries, the female warriors who flew over battlefields to choose which slain heroes would be taken to Valhalla. The shimmering lights were the gleam of their armor as they rode across the sky. In Finland, the lights have a wonderful name: Revontule, which translates literally to fire fox. The legend says a mythical Arctic fox runs so quickly across the snowy fells of Lapland that its bushy tail brushes against the mountains and fells, sending a shower of colorful sparks up into the night sky. For many indigenous peoples of North America, the lights were deeply spiritual. The Cree believed they were the dance of the spirits, the souls of the departed. When the lights were bright and active, it meant their ancestors were happy, perhaps communicating with them. The Algonquin people believed the lights were a great fire built by the creator, Nanabojo, to remind them that even after he had moved far to the north, he was still thinking of them. But the lights weren't always seen as a positive. In some cultures, they were a fearsome omen of war or plague. People would tell their children to be quiet and stay inside, for fear that the lights, seen as spirits, might come down and carry them away. From divine battles to the souls of the dead, every culture touched by the aurora created a story to explain it.